In the previous lecture and this one, I am trying to prove a central theorem about projective representations. The theorem essentially says that there is no intrinsically projective representation of a given group if the following two conditions hold. All generators of the corresponding group, that is the elements of the Lie algebra, can be redefined by shifting by real numbers, or actually real numbers times the identity, to eliminate all central charges. That is, for the shifted generators, you don't have any element in your Lie algebra which commutes with all other generators. In addition to that, the other condition that has to hold is that the parameter space of the group is simply connected. In the last lecture, we made considerable headway towards the proof, but some very important details are still left out, and we are going to fill in those in this lecture. Let me remind you of what we have done so far. What we want is to show that under those conditions, you can always find unitary operators U corresponding to every symmetry group element or Lie group element T, such that U of T of beta times U of T of alpha will be equal to U of T of F of beta comma alpha. Remember, here we are dealing with a Lie group with parameters alpha 1, alpha 2, alpha r for the elements. That is, for one of the elements, the other one has elements beta 1, beta 2 up to beta r. And when you combine two such symmetry group elements, the corresponding product has as its parameters the results of the function f, which is a vector valued function acting with beta and alpha as its two arguments. Now, in order to show that such a representation is always possible under the conditions that I mentioned, what we first did was to lay down somewhat arbitrarily standard paths in the Lie group parameter space which go from the origin, that is 0 values for all the parameters, to a particular parameter value, let's say alpha vector, alpha 1, alpha 2 up to alpha r. And this standard path we are calling theta with the alpha subscript of s. As the parameter s goes from 0 to 1, the map traces out as its image a curve on the parameter space which goes from the null vector, that is the origin, to alpha vector. Let me remind you that the origin in parameter space stands for the identity element of the group. What we do next is that we solve a differential equation which U alpha of S, an operator valued function, obeys, and that differential equation essentially involves the generators and quantities called HAB along with the derivative of theta with respect to S, that is how fast are the parameters changing along the space. We justified the reasoning behind this particular differential equation in the last lecture, and our hope is if we solve this differential equation subject to the initial condition that U alpha at the origin at 0 vector is the identity, then the resulting U alpha at 1 is going to be our U of T of alpha. Of course, the hope is that our U of alpha of 1 is going to obey the composition rule which the non-projective representations should obey. That is, U of alpha of 1, when you multiply it by U of beta of 1 from the left, you are going to get U corresponding to F of beta comma alpha at 1. Remember, so far what we have said is, if we integrate our differential equation along the standard paths, at the endpoints we will land up with some operators which we hope will obey this particular rule. Now, in order to see whether that is true or not, let us try to think about this particular picture. Here we have denoted, along with the origin and the point alpha, several other points and standard paths in parameter space. You have the blue path which goes from the origin to beta, that's a standard path. Then we have an orange path which goes from the origin to the composite parameter value f of beta comma alpha, again that's a standard path. what we have done in order to go through our proof is the following. We have chosen a different path to go from the origin to the final point f of beta comma alpha, and that path has been defined by going along the standard path to alpha in the first half of the parameter values from 0 to half, but of course we have done that twice as fast. And then the next half, we have imagined the point traveling along the standard parameter path to beta and compose the parameter value that we get there with alpha using f to get the light blue path. Now, what we had shown in the last lecture is that if we go along this path curly p, then u of curly p at 1 is exactly equal to u of beta at 1 times u of alpha at 1. And this is a major step towards the final result. The only problem, as I explained at the end of the last lecture, is that u of curly p at 1 is for a non-standard path. But is there a guarantee that this value that we end up at the end of the path curly p, green plus the light blue, is the same as the value of u that we would get if we were to solve the same differential equation along the orange, the standard path? The answer to that question is going to occupy us here. So what we really want to check is whether the value of u at the end of a standard path depends only on where we end up, the parameter value we end up at, or does it depend actually on the particular path taken. So what we will do is we will try to explore what happens to the value of u at the end of a path if we vary the path slowly, but keeping the two endpoints fixed. So let us go back to our original standard path, which goes from 0 to the parameter value alpha. Of course, what will work for this particular standard path will work for all paths. So this is just one particular path that we have chosen. The green one, the dark green one, is our original path, and we consider a changed path, the dark blue dashed one, theta prime alpha of s, and we go from theta alpha of s to theta prime alpha of s by a series of very small changes. What we have shown is an intermediate stage in this process. The light green path is an intermediate path, theta of s, and from that we have shifted by delta theta of s to go to the light blue path. So theta s plus delta theta of s is a function on the light blue path. Our aim is to figure out exactly how the u at the end of the path changes while keeping the differential equation the same for each one of the paths as you go from the dark green path to any of the neighboring paths or any of the paths which you can go to by making small shifts like this. Remember, for each one of these paths, u actually obeys this. So I will just drop the alpha here because I am talking of any intermediate path as well. dds of u of s is ita times u of s times hab at theta of s, whatever theta function that intermediate path is described by, times d theta b ds. And the question is, exactly how much does u change when you go from one path to the same parameter value along a neighboring path? So you change theta of s to theta of s plus delta theta of s, and you are asking how much does u change. The answer to that is sort of obvious. This is a differential equation, so you have to solve the differential equation for delta u now. And to find out the differential equation for delta u, all you have to do is remember that on the right hand side you have three things which will change when you change over to a neighboring path. U will change to u plus delta u. HAB will change because HAB depends on the point in parameter space where you are, and when you go to a neighboring path, that point changes. And of course, the neighboring path will have a different slope, so d theta b ds will also change. Putting these together and making use of elementary calculus, basically Leibniz rule for products, you end up with the following. Rate at which delta u will change along the path is given by three terms. In one, you have just u changing to delta u, the rest staying the same. In the next, u and the slope d theta b ds stays the same. HAB changes, but HAB changes because its argument change. So this becomes HAB comma c. This is really nothing but derivative with respect to the theta c component at theta times change in theta c. And finally, you have a term which is there because the slope has changed. This is really delta of d theta b ds, but that is the same as ds of delta theta b. Now, if you take a look at the first term here, what we will do next should be pretty familiar to those of you who have studied any kind of variational method in mechanics or optics or wherever. What we will do is change this last term into basically a total derivative. So, IU inverse TAU HAB theta d ds of delta theta b, which is the last term, becomes dds of I u inverse TAU HAB at theta delta theta b. Well, this obviously is not correct. What we need to do is subtract from this two derivatives. One is the derivative of HAB with respect to S. That of course is once again HAB comma C at theta del HAB del theta C times d theta c ds times of course the rest of the stuff. And another term which involves the derivative with respect to S of U inverse TAU. This is obviously Leibniz rule used again. Now note that the second term that we have here, the one with HAB comma C d theta c ds delta theta b, is almost the same as the term that we had in the expression for U inverse d delta u del ds at the top of your screen. This term, but if you look closely, there is a difference apart from of course the sign. Although the two terms almost exactly match, note that the C and B indices on this are interchanged in position. That is, in one you have d theta b ds delta theta c, in the other you have d theta c ds delta theta b. Bear this in mind when we couple these terms together. That will be important. But for the time being, let us focus on this particular derivative of U inverse TAU. Now for later convenience, I've just decided to take a look at the derivative of U inverse TEU, where E is some other index. So dds of U inverse TEU is simply this expression, which follows from Leibniz rule once again. And note that TE of course does not depend on the parameter S. Now, a small bit of manipulation is needed before you can cast this into a more tractable form. All you do here is add a U inverse U at the beginning. That of course is the identity that you can always multiply something by. But then use the fact that U du inverse ds is negative of du ds U inverse. And thus, you can write everything in terms of du ds. And that of course is great because we already have an equation for du ds. Now, you can easily notice that this is nothing but the commutator of this quantity U inverse TEU and this operator U inverse du ds. That's what this whole expression is. And so, using the differential equation, we land up with this fact that it's actually the commutator of U inverse TEU with I U inverse TDU HDC d theta c ds. Note that here again we have changed the dummy index from A to D, again for later convenience. So it's very easy to see that this commutator is the same as I times U inverse times the commutator of TE and TD, then U, and these are of course just numbers which have come out of the commutator bracket. TE comma TD is simply according to the standard rules of Lie algebra given by I times the structure constant C AED TA, and using that, this is exactly what the derivative becomes. Let us now use this derivative that we have just calculated to rewrite the third term in our expression above. So, if you take a look, this was our expression which I have just rewritten here, and all I have done is we had U inverse TAU HAB theta delta theta B in the last term, where I've just changed the dummy index from A to E so that we can directly use this expression, which is dds of U inverse TEU. Now, if I just plug this in, this is what I'm going to get. All I have to do is get rid of this term, and instead of it, bring in this term. Note that the minus sign here simply changes the minus I to plus I. TDS of U inverse TEU, which is this expression, is written here, but in pieces. So let me just point out what the pieces are. U inverse TAU, that's here. CAED, check. HDC theta, check. D theta C ds, check. Of course, our expression, in addition to the derivative, had HEB theta, this one, which we have, and delta theta B, which we have. So, you should be able to convince yourselves that this is exactly the same as a term which I already had here. Now, let me go back to what we started out with. This is what we actually had. U inverse dds of delta U is minus du inverse ds of delta U plus this term plus this additional piece, which we could rewrite simply in this format. This is just bringing the minus du inverse ds delta U to the other side. Then you have this term which is the same as this one, and of course this term which I have replaced by a total derivative with two more terms to compensate. Now we can collect everything together. In fact, note that we went through all that dummy index changing gymnastics simply so that we get the same terms U inverse TAU and delta theta B d theta C ds everywhere. Although you may have spotted something that I have just pulled quickly over you. You originally had a delta theta C d theta B ds here. So in order to get the same form for the multipliers in each of these three extra terms, the terms outside the total derivative that is, what I have done is I have changed the dummy indices here. I've interchanged B and C so that this term becomes HAC comma B. Now, we can directly couple things together. Moving all the total derivatives to one side, we get dds of U inverse delta U minus I U inverse TAU HAB theta delta theta B equals the sum total of the three other terms, which simply becomes I U inverse TAU delta theta B d theta C ds multiplied by a combination of these terms. HAC comma B minus HAB comma C plus CAED HEB HDC. Of course, all of this is evaluated at theta, at the intermediate point, whatever parameter value that has. Now this really looks quite intimidating, and it is, frankly. But you would of course be very relieved to know that the right hand side simplifies drastically. In fact, the right hand side is exactly 0. At this point, it is sorely tempting to leave the proof that the right hand side vanishes as an exercise for the reader, or in this case the viewer, and proceed with examining what the consequences of the vanishing of the right hand side would really be. However, that would be unfair. So let us keep the equation proper at abeyance for the time being and take a look at this particular part of the expression. It will follow from Lie group theory that this expression actually vanishes. Now this part actually gave me a huge amount of trouble. In fact, I spent 3 days trying to prove this. Not that it's really that difficult, but there is a reason why I took 3 days to come to the final answer. The proof, that is. And I will explain why it took me 3 days. But what we have to do is start from what we already know about the composition function f for Lie groups. From associativity, we had already shown this result, which we had used in the last lecture. The function fa, which tells you how group parameters combine to give the parameters for the combination element, obeys this particular property that if you differentiate the th component with respect to the first argument's bth component at any arbitrary point, then it's related to the derivatives, similar derivatives taken at theta2 equal to 0, or the first argument equal to 0 to be more precise, by this kind of expression. This is the equation that we used earlier to prove, earlier meaning in the previous lecture, to prove that u curly p at 1 is actually u beta at 1 times u alpha at 1. What we are going to do now is we are going to differentiate this once again with respect to the first argument, or rather one component of the first argument, and then set the first argument, all its components, to 0. We have to be a bit careful about the indices here. Note that C and B are free indices and A is a dummy index. What we want to do right now is differentiate with respect to an arbitrary component of theta2. So we have to be careful that we do not call that component's index either A, B, or C. So let us just use D. So we are going to differentiate both sides of this expression with respect to theta to D first. So what we are going to get is straightforward. This is just straightforward differentiation. This product gives you two terms. One of them is del 2 fa del theta 2 b del theta 2 d at theta 2 theta 1 times hca at f of theta 2 comma theta 1. Added to this, you have this term intact plus the derivative of this with respect to theta 2 d. But note that hca depends on theta 2 d only through the f. So basically, what you are going to get is the derivative with respect to the eth component of its argument, which is fe. Then you have to multiply it by the derivative of fe with respect to theta to d. This is just the chain rule being used here. And on the right hand side, you of course get hcb comma d. That's comma, of course, is just the derivative with respect to theta 2 at theta 2. Note that after this, what we want to do is put theta 2 equal to 0. And that simplifies this expression considerably. You end up with this second derivative evaluated at theta 2 equal to 0 times this expression, which when theta 2 is 0, f vector simply becomes theta 1 vector. So this is just HCA at theta 1. This derivative, when you put theta 2 equal to 0, simply becomes h bar AB at theta 1. H bar, remember, is the inverse matrix, the matrix of the original derivatives, so to speak, whereas H is its inverse. Then you have HCAE at f of theta 2 comma theta 1 with theta 2 equal to 0 is just theta 1. This expression is by definition h bar ED at theta 1, and the right hand side becomes HCB comma D at 0, which we have already figured out in the last lecture is minus FCBD, where FCBD is nothing but the coefficient of the second order mixed term when you expand out FC in a Taylor series in theta and theta bar is two arguments. So now, this is where I started to have trouble, because Weinberg had given a very simple expression for the next step. What Weinberg had simply said is that you can invert this expression to get HCA comma E. He didn't use exactly those indices, but that's what he really said, that HCA comma E is simply what you can get by using the inverses of these two, or components of the inverse matrix, to get rid of these two terms, that is multiply by HBA and HDE again at theta 1. In what follows, I'm going to just drop the theta 1 argument, because that's the only argument which these quantities have, and that's common throughout. Now, what Weinberg had written down is the following. HCAE is simply minus FCBD, HBA, HDE. And for the life of me, I couldn't figure out how that could be true, because this term is very much there. It does not vanish for a general Lie algebra. It may vanish for some specific Lie algebras. In fact, for a few simple ones it does. However, there is no reason why this second derivative term should vanish. So the actual expression that you really have is this. HCAE plus del 2 FA del theta 2 B del theta 2 D at theta 2 equal to 0 times HCA. Now, the problem is here A is a free index and this A is a dummy index, so we need to change that. I changed that to P. So you have del 2 FP HCP, and then you have HBA times HDE, which we'll get rid of the H bars here. And that is equal to minus FCBD, HBA, HDE. Now, the final result that we need, the vanishing of that right hand side of our differential equation, critically depended upon this. In fact, that's what it seemed, because Weinberg used this expression, this equal to the right hand side without this term, and used it to prove that the right hand side of our differential equation vanished. Now, I was sure that I was making a mistake somewhere, so I kept on checking and rechecking my work using various different approaches, and it took me quite some time to get convinced that frankly Weinberg had omitted this extra term either by mistake or by a typo. What transpires though is that it really doesn't make a difference to the final answer, which is what took me quite some time to figure out. So before I go there, let me just point out that in our original expression, if you remember that, we had HA C comma B minus HAB comma C. So let's just change our indices a bit so that it will be easier to recover that expression. So here C, A and E are the free indices. P, B, D are dummy indices. What we will do is we will just be careful and change our indices properly. We will change the C to A everywhere. We will change the A to C everywhere. So everywhere we are just going to interchange A and C. But we are also going to change E to B, which will now become a free index. Of course, if we do that, all the B's here would have to be replaced, and we replace that with E. So del theta to E, H, E, C, because remember, I've interchanged A and C. This C here, HCP, becomes HAP, this becomes HEC, and HDB, because the E in the previous expression has become B here. That may seem a bit confusing if I just rattle it off, so it's best that you take pen and paper and convince yourselves that this is the correct expression. We did the same thing on the other side, taking care not to mix up indices and so on. So this is the term which gave me a lot of trouble, because Weinberg was claiming that HAC comma B is equal to this, and there was no sign of this term. But note that what you really need is not HAC comma B, but the difference between HAC comma B and HAB comma C. So what I will do now is just rewrite that expression once again, interchanging B and C. So that's what we have done on both sides. Here B and C have been interchanged. Now note the beauty of all this. If you look at this expression, here of course it looks like the expressions are different because everything else is the same between this term and this one. But you have C and B here and B and C here. And C and B are not even dummy indices, so we cannot really interchange them. But the E and D, which go with the B and C, are actually dummy indices. So we can interchange them. We can change this E to a D and this one to a E. Of course, we have to do it consistently throughout. D, E. But now note that the multiplier here has now exactly matched the multiplier here. We have HDB, HEC, exactly as we had here. And the mixed second derivative that you have in the front here has changed formally, but mixed partial derivatives like these are equal. So these two terms are actually exactly equal to each other. So when you subtract the two, this term and this term just drops out. So even though Weinberg had omitted this term in his expression in the book, that really did not make a difference to the final answer, because this would cancel anyway. I'm sorry to say it took me quite some time to figure this out, especially because I was convinced that Weinberg was right, so I must have been making some mistake, which turned out not to be the case. On the other hand, what happens to the right hand side here? We can of course take the FAED common between the two terms, so that I can write down the right hand side as FAED times HEB HDC minus HEC HDB. However, it's much more useful to rewrite this in a slightly different fashion by interchanging the D and E indices in the top expression. So this becomes DE and this becomes D, this becomes E. Of course, now the multiplying factors of H in both terms are exactly the same, namely HDC times HEB. And so when you subtract, you end up with this expression. HAC comma B minus HAB comma C is simply FAED, that becomes a plus, minus FADE, HEB, HDC. Now this is very useful, and we are actually near the end of our derivation, because what happens is that this is exactly the structure constant CADE or negative of CAED. So putting all this together, we end up with HAC comma B minus HAB comma C plus CAED HEB HDC equals 0. And this exactly was what was on the right hand side of our final expression. In other words, this is what you had, and this term is 0. So what you land up with is U inverse delta U minus I U inverse TAU HAB theta delta theta B is constant along the path. It does not change as S changes. Okay, but it still looks like a pretty complicated expression. But note that at the beginning of the path, you must have U equal to the identity. So when you go to a neighboring path, at the beginning, U is still the identity. So delta U is 0 there. So at S equal to 0, delta U is 0. But so is delta theta B, because you're not allowed to change the beginning or the end point of these paths. So, at the beginning of the path at S equal to 0, this quantity must be equal to 0. And hence, being a constant, it has to be 0 throughout the path. What is extremely important for us is that at the end of the path, this whole expression is still 0, of course, but there, delta theta B is again 0 because you're not allowed to change the endpoint. So this term drops out at the end of the path at S equal to 1. So at S equal to 1, we end up with U inverse delta U equals 0, and that immediately tells us that delta U is 0. So U alpha 1, this quantity, is stationary under any infinitesimal variation of the path that leaves the endpoints fixed. So if I can go from one path between 0 and alpha to any other path between the same two endpoints by continuously moving from here to here, of course staying within the parameter space all the time, then at the end of each one of these two paths, you will end up with the same value. So you are fully within your rights to interpret this quantity as something which depends only on the parameter value and not on the path itself. And then, once you have made this identification, U alpha 1 is UT alpha, you can immediately write down from U curly P1 is U beta 1, U alpha 1, the result that on the right hand side you have UT beta, UT alpha, and on the left hand side what you have is UT of f of beta comma alpha since the path curly P ends at f of beta comma alpha. And as we have just proven, the value of this unitary operator U, which you get as a solution to the differential equation, depends only on the endpoints and not on the actual path followed. But hold on a bit. There is one very important thing that I have just skipped over here. The important thing is we should be able to change one path into another by a succession of infinitesimal variations. Only then will U alpha 1 for the first path be the same as U1 for the final path. So this path independence comes with a caveat. This will work only if you are able to change any path from 0 to a fixed parameter value, let's call that an arbitrary parameter value theta, to another path which goes from 0 to theta continuously without ever leaving the parameter space. And just to be clear, I have put in arrows to show which way we are traversing these paths in both cases. Note that this has to be true for all paths which join 0 to theta for this proof to work perfectly. Now this is exactly what we mean when we say a manifold, or the parameter space here, is simply connected. Now usually we define simple connectedness in a slightly different manner. We say that it is the ability to shrink any loop to a point. But the fact that these two statements are equivalent is very easy to see. Let us first start with the statement that any two paths starting from the origin to a given point can be deformed continuously into each other. Then we can have a loop starting at the origin, which goes back to the origin of course, and just choose any arbitrary point on this loop as your second part. So of course the loop is being traversed this way. Now you can actually think of this as two distinct paths. One starting at the origin and going to this point which we label theta along this part, the other going back. But notice that according to our assumption, we can of course deform this part continuously into any other path going between 0 and theta. So in particular, we can deform it to a path which looks like this. And of course, I can't draw it that precisely, but ultimately, we can make it completely merge with the other half of the black path just going the other way. So what we had was this loop made out of this path and this path. And what we have done is we have continuously deformed this part until it becomes exactly this one. So now our loop has become a path traversed from 0 to theta along the black line, but in this direction, and then back to the origin. And this one can of course be shrunk down to a point staying throughout within the parameter space by making it just smaller and smaller. So at the intermediate state you go like this and go back, then you go like this and then go back, and so on until it shrinks down to a point. So we have managed to show that if you could deform any two paths starting from the origin to a given fixed point into each other, you can actually shrink any loop starting and ending at the origin, or at least a loop for which the origin is a point on it, to a single point, that is the origin itself. There's nothing special about the origin, but for mathematical purposes, especially for setting up the fundamental group, as we will briefly touch upon later, keeping one point fixed is usually a nice idea, and this one point can be conveniently taken to be the origin. Now the converse of this fact, that if every loop can be shrunk down to a point, then any two paths starting from the origin to a given fixed point can be deformed into each other, can also be proven in a pretty straightforward manner. Now the upshot of all this is, if the Lie algebra corresponding to a Lie group does not have any central charges, or at least has central charges which can be shifted away, and the group manifold is simply connected, what we can always do is construct a non-projective representation. That is, one that obeys u of theta bar, u of theta is u of f of theta bar comma theta. I've changed my notation somewhat. I'm just dropping the vector signs on the parameters, because by now it should be obvious that we are not talking about a single parameter usually, but a bunch of parameters. Now, what remains to be shown is that any projective representation, any representation which obeys u tilde theta bar u tilde theta, is e to the I phi theta bar comma theta times u of f of theta bar comma theta. That is, any representation which has this extra phase factor is connected to the non-projective one that we have just constructed simply by phase shifts. That is, any projective representation that we can have is actually trivially projective. To show this, we will take the inverse of this equation and multiply this equation at both sides of this equation by the inverse of this one. And this will lead us to this relationship. u theta inverse u theta bar inverse, that's of course the inverse of this, times u tilde theta bar u tilde theta has to be u f of theta bar comma theta inverse times u tilde f of theta bar comma theta multiplied by the phase factor into the I phi theta bar comma theta. Now, you must have spotted a mistake that I made a while ago. The right hand side here must be u tilde f of theta bar comma theta and not u f of theta bar comma theta. And that of course is why you have an u tilde f of theta bar comma theta here. What we will do next is we are going to differentiate both sides of this equation with respect to one component of theta bar, let's say theta bar b, and then set theta bar equal to 0. Let us first see what that does to the left hand side of this expression. In order to do that, we must remember that from the expansion, u of theta bar equals identity plus I theta bar b tb plus half tbc theta bar b theta bar c and so on, it's easy to see that if you differentiate u with respect to theta bar b, you get itb plus higher order terms which all have theta bar b in them. If you then put theta bar equal to 0, you are left only with itb. And it's very easy to see that for u inverse, a similar derivative will lead to minus itb. And that can be easily used to differentiate the left hand side of this expression here with respect to theta bar b. Of course, one term will come from differentiation of this. You will get a minus itb from that. And the other term will come from a differentiation of this, which will give you a plus itb. Of course, in the rest, what you're doing is you're going to substitute theta bar equal to 0, and that leads to both u tilde 0 and u0 being the identity. By the way, let me remind you that both u and u tilde are built out of the same generators. As a result, the derivative of both del u and del u tilde with respect to theta bar b is exactly equal to itb. Now, although u tilde theta bar and u theta bar are different in general, but once you put theta bar equal to 0, they both give you the identity. So basically these terms are effectively not there, and so this and this just cancels out, and you are left with 0 on the left hand side. Thus, if you differentiate the right hand side of this expression with respect to theta bar b and then put theta bar equal to 0, you must get the same thing that you get from the left hand side, namely 0. So, this is the expression that you expect. Of course, this is nothing but differentiation of the right hand side with respect to theta bar b and then setting theta bar equal to 0. Now, to proceed further, what we will do is we will define this quantity u theta inverse u tilde theta, this unitary operator, as v of theta. And so, our expression that we have found out right now simply becomes derivative with respect to theta bar b of v at f of theta bar comma theta times e to the I phi theta bar comma theta at theta bar equal to 0 must be equal to 0. Note that what we want to prove ultimately is that u tilde theta is related to u theta by a phase shift. And that means that what we want to prove ultimately is v of theta is just a simple phase factor times the identity. The phase factor of course might very well depend on theta, but other than that, it's just a simple phase. Now, in order to prove this, what we will do is simply carry out the differentiation. Note the chain rule simply tells us that when you differentiate v of f theta bar comma theta with respect to theta bar b, what we will do is first differentiate this with respect to f of a and then multiply this by the derivative del fa del theta bar b. By the way, I've been saying multiply this by, but as you must have realized, I also mean a sum over the repeated index a in all such expressions that we have seen so far. Of course, that times e to the I phi theta bar comma theta plus this term stays intact. You differentiate this to get e to the I del phi del theta bar b at theta bar comma theta e to the I phi theta bar comma theta. Now, what you need to do next is set theta bar equal to 0. That is, all the components of theta bar must be set equal to 0. Let me remind you that theta bar equal to 0 essentially means u of theta bar is identity, and that immediately means that phi of theta bar comma theta for theta bar equal to 0 must be 0. This is something which we used in the last lecture as well. And that means this factor here just becomes 1. On the other hand, if you set theta bar equal to 0, f of theta bar comma theta simply becomes theta. So this derivative now becomes del v of theta del theta a times this derivative at theta bar equal to 0 is our old friend h bar ab. So what we have is the following: del theta a of v of theta times h bar ab of theta times 1, of course, from here, plus I del phi del theta bar b at theta bar equal to 0 times v of theta times 1 equals 0. And just by using the inverse matrix H of h bar, we can rewrite this in the following manner. This simply becomes del theta a of v of theta plus I times h ba of theta. That's the inverse of h bar being used here, times del phi del theta bar b at theta bar equal to 0 times v of theta. So what we will do next is just call this combination, which of course depends only on theta and has only one index, namely a, b being a dummy index. We will define that to be phi a. So phi a is not the original phi, or it's not the derivative of phi with respect to a. It's actually del phi del theta bar b at theta bar equal to 0 multiplied by hba of theta. And with this abbreviation, this equation simply becomes del v del theta a plus I phi a. This whole combination is phi a times v of theta equals 0. The next step is pretty straightforward. All I do is differentiate this expression with respect to theta b. And therefore, you end up with del 2v del theta b del theta a plus I del phi a del theta b times v of theta plus I phi a del v del theta b. But we already know that del v del theta b is I phi b v theta with a minus sign. And we just plug that in here instead of del v del theta b. And that gives us del 2v del theta b del theta a plus I phi a del theta b v of theta plus phi a phi b v of theta equals 0. Now we're to interchange a and b in this expression and subtract the two. You will immediately see that this term will cancel out, so will this term, and you will be left with I times del phi a del theta b minus del phi b del theta a. This whole thing multiplied by v of theta equals 0, and since v of theta being unitary is an invertible operator, you immediately end up with del phi a del theta b minus del phi b del theta a equals 0. Now this should remind you very much of the curl that you studied in first year vector analysis, or if you have studied higher differential geometry, that is exterior derivatives of differential forms, this would look very much like the derivative of a one form. Anyway, if you cast your minds back to your first year vector analysis days, you would immediately realize that this expression can be trivially satisfied if there existed a function rho such that phi a is del rho del theta a. Then the vanishing of this expression is nothing but the fact that mixed partial derivatives are always equal. Now the converse of this statement, that if del phi a del theta b minus del phi b del theta a equals 0, or exterior derivative of one form is 0, then if the space is simply connected, simple connectedness comes in once again, we know that there must exist a function beta of theta such that phi a is del beta del theta a. Note that if phi is the gradient, then its curl is always 0. That's basically what is being used here, only in R dimensions, not just in 3. But that was the trivial part of the statement. The non-trivial part is the curl inverse is also true. Back to our 3-dimensional analogy. If curl of a vector field is 0, it's always the gradient of a scalar field. That's not necessarily true really. That's true only if the underlying space happens to be simply connected. So for this simply connected space that we have assumed, phi A is given by del beta del theta A. And therefore, if I just go back to our original equation, del del theta B of V of theta plus I phi B V of theta is 0, and plug this thing in, assuming that our space is simply connected, so that phi B is del beta del theta B for some function beta, you end up with this expression, and multiplying both sides of this expression by e to the I beta of theta immediately shows that this is nothing but del del theta B of e to the I beta of theta times V of theta, and that has to be 0. Thus, V of theta times e to the I beta of theta, which of course is u theta inverse u tilde theta e to the I beta of theta, has to be a constant, and it's obvious what the value of this constant is. The value of this constant has to be its value at theta equal to 0. And at theta equal to 0, of course, both u of theta and u tilde theta are identities. And e to the I beta of 0 is just some constant phase factor. So this constant has to be equal to e to the I beta of 0 times identity. And a simple rewriting of this expression tells you that u tilde theta has to be u of theta e to the minus I beta of theta, which you bring to the other side, plus beta of 0. Thus, if you just shift the phases of the unitary operators, in fact, if you shift them by e to the plus I beta theta minus beta 0 to go from u tilde to u, then you will end up with a non-projective representation. This then wraps up our proof of the following statement. If the Lie algebra is or can be made by a shift of the generators, free of central charges, and the group manifold is simply connected, then there are no non-trivial projective representations. We can construct a non-projective representation, and all projective representations can be reduced to that one. Now, in order to look at this a bit more deeply, let us ask ourselves this question. What if there are no central charges, or we could shift the central charges away, but the group space is not simply connected? Now this becomes a very, very important question for physics, because this situation is there in many important cases. For example, the rotation group happens to be non-simply connected, and the same is true for the Lorentz group, which of course has rotation group as a piece of it. So to understand this, let's go back to what we talked about in the last lecture. Consider this situation that we have standard paths, the green one, the orange one, and the blue one, leading to theta 1, f of theta 2, theta 1, and theta 2 respectively. And we also have this other path curly p, which you make out of partly traversing the standard path for theta 1 and then traversing the standard path for theta 2 and combining that with theta 1 using f, and you get this sky blue path. I've described this in some detail in the last lecture. But let's suppose that our space is not simply connected. If it were simply connected, you could deform this curly p path, the green light blue path, continuously to the orange path, and what we have argued today is that would show that whatever unitary operator you calculate by going along this particular path actually is the same as whatever unitary operator you get by solving the differential equation along the orange path, the standard path. Now, let's say curly p cannot be deformed into the standard path to f of beta comma alpha because our space is not simply connected. In other words, the loop that you can form with the green line, the sky blue line and the orange line, by traversing the orange line backwards of course, here cannot be shrunk to a point. Now in this case, you can no longer guarantee that u inverse f of theta 2 comma theta 1 times u of theta 2 comma u of theta 1 will be equal to 1. What you can guarantee is that u inverse curly p of 1 times u of theta 2 times u of theta 1 is 1, but u inverse curly p of 1 is no longer necessarily equal to u inverse f of theta 2 comma theta 1. So you might very well get a phase factor. Now, what is important is that this phase might definitely be non-zero, but it has to be the same for all loops that can be deformed into each other while keeping the origin fixed. So if you can think of any other path here, you would end up with exactly the same phase factor for this one, as long as you can deform that new loop into the original loop. Now this brings us to a very important concept in algebraic topology. The set of all loops to the origin which can be deformed into each other, this particular set, is called a homotopy class. I am not going to describe algebraic topology, in particular the fundamental group, in great detail here, simply because that topic is big enough to warrant an entire lecture by itself. However, what I will just point out is that the phase factor phi here will depend on the homotopy class of the loop. That is, all loops which can be deformed into each other belong to the same homotopy class. For each of them, you will have one and the same value of phi. That's exactly what we have proven a while ago. However, if two loops belong to two different homotopy classes, then the phi can very well be different for them. Now, what is very important is the statement from algebraic topology that the homotopy classes of loops actually form a group. Of course, in order to define this group precisely, you need to lay down rules for combinations of the group elements, that is, how to combine one homotopy class with another and so on. Once again, this will take too long to describe here. I'm just going to tell you the result here. This particular group is called the fundamental group of the parameter space, also called the first homotopy group of the parameter space. And these phases that we have, you have one such phase for each loop, and it takes a bit of thought, but if you combine two loops one after the other, that is, you traverse one loop, then you traverse the other loop, you will end up with the two phase factors being summed up. And this is technically represented by the statement that the phases that you get here for projective representations provide a 1D representation of the fundamental group. So in order to understand what kind of non-trivial phases you can have for a projective representation in the presence of a non-simply connected parameter space, and let me stress once again, in the absence of central charges, you have to look at the first homotopy group. In particular, you have to look at its one-dimensional representations. So for those of you who are acquainted with a bit of group theory, this should give you a very solid understanding of what kind of projective representations are actually possible. Well, in the all-important case of rotations or Lorentz transformations, you will see that the structure of the fundamental group is really so simple that we don't really need the help of full-fledged representation theory to understand all possible phases of projective representations. They can be understood by simply applying some thought. We will talk about the Lorentz group in particular in what is going to come.